Swayam Prabha. Digital India. Educated India.
So what we will do is we will now try to develop a treatment which is a little more involved, and we are going to use character tables. Before that, what is the symmetry point group of BH2? D infinity H. Have we discussed the D infinity H character table? I have forgotten. We have not. So let us do that. This is the D infinity H character table. Can you see? What is it that strikes you first? Yes, it is complicated, of course. And also the names are different. Mulliken symbols are different. They are different to emphasize the fact that these are special kinds of groups. So instead of A, B, etc., you say sigma, pi, delta, etc. Okay. Let us see what we have here. What are the symmetry elements present in D infinity H? First is the C infinity axis, right? So now if I rotate it, if I rotate the molecule about the C infinity axis by say 0.000000000001 degree, is there a symmetry operation? Think of a C3 axis. If I rotate by 10 degrees, is there a symmetry operation? No. But about C infinity axis, if I rotate by something that is as close to 0 that you can think of, even that is a symmetry operation, right? So which means that infinite number of symmetry operations will be associated with C infinity axis. So that is why you have something like this, C infinity phi. What is the meaning of C infinity phi? Phi is any angle. Because you can rotate this way or this way. Of course, it is kind of redundant because when you rotate this way, you can go all the way and reach there also. But this is a convenient way of writing it. After all, twice infinity is infinity. It is true to emphasize plus and minus rotation.
When we take C3, we take 2C3 because we can do 2C3 operations. So here there should be infinite C infinity operations because we can do infinity.
There are infinite C infinity operations, that is right. But what we are showing here is that this is C infinity to the power phi. No? So you want to write everything. So plus phi and minus phi. Then you can write 2 phi, 3 phi, 4 phi, whatever phi you want. So that's why it gives you infinite number. That's what dot 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 means. Then you have sigma v. Once again, you might as well call it sigma d. Sigma v, infinite number of sigma v's. Where are the sigma v's? This. My palm here is sigma v, right? Okay. Then what do you have? Infinite number of centers of inversion. Then one point of inversion. It cannot be infinite number of points of inversion. Okay. The center of the bond is the center of inversion. Okay. Then once again, like C infinity, you can write S infinity also, same thing. And finally, you have infinite number of C2s. There are more than one ways of writing these D infinity H character table. If you notice, one symmetry element that is missing very prominently is sigma H, right. So, there are ways in which you could incorporate sigma H also, but it does not matter, you follow any one convention, it will work. After all, you have infinite number of symmetry operations. Okay. So, C2, how many C2s are there? Once again infinite, this is a C2 and you can just turn it by whatever angle you want, infinite number of C2s. Okay. So, now the simplest case is of course, so what will be the total number of irreducible representations? Infinite. So, how many one dimensional representations? How many two dimensional representations? So, what we do is we only concern ourselves with a minimal description of the point group. We only discuss the IRs that usually show up and we usually use, and these are those IRs: sigma g plus, sigma g minus, pi g is a two dimensional representation, delta g is a two dimensional representation, and then you replace all the g's with u's, you more or less get another set of representations. You could go on writing, if you have time, you could go on writing all the different kinds of representations, but these are the 8 representations that we most commonly use. So, these are the ones that are usually written. Okay. What is sigma g plus? All characters are 1. So, totally symmetric representation. What is the molecular name that we usually use for a totally symmetric representation? A1 or A1G or A1G dash, so on and so forth, or AG dashed, depending on the molecular, depending on which molecule you use, depending on which character, which symmetry point group you use. Yes, sir.
Why not there is a plus or minus sign on the pi u or pi g?
Because it is not required. We only need to consider one pi g and one pi u. Okay, you can actually write plus minus, but as we had discussed earlier also, sometimes if you don't need the dash, you don't write it, right. So, you are perfectly fine if you write plus, no problem with that, but we don't need it, that is why we write only what we need. Okay. So, these are all, so this is something that you can see very easily, right, that these first 4 have all plus characters of with respect to I. So, 1 1 and these are two dimensional representations, so these are 2. And u's are all minus 1, here it is 0. So, there it is a little more complicated, fine. So, what is the second sigma? Sigma g minus. Sigma g minus has a minus 1 for sigma v and minus 1 for C2. Pi g and delta g are, the pi and delta are two dimensional representations. Now, tell me, the sigma, pi, delta, do they remind you of something? So, sigma bond, pi bond, delta bond have got their names from here. We have been talking about sigma bonds from class 11, right. So, sigma bond, pi bond, delta bond actually get their names from here because they belong to these symmetry species. Okay. So, what we are now going to do is that we are going to work out the symmetry species of the molecular orbital, and we will see that they are going to belong to some irreducible representation here or the other. Okay, fine. So, the way to go about is this: E 2C infinity phi, 2C infinity phi, and dot 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 infinite number of sigma v's I 2s infinity phi dot 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 infinite number of C2s. So, what we will do is, now we will try to generate the reducible representation of the SALCs. Do not forget, SALCs are generated by using atomic orbitals of the pendant atoms, hydrogens in this case. Okay. So, the way all our discussion today is from Carter's book. Cannot read? Okay. Carter, it is there in the library. what Cotton has done is that he has gone on directly to something called projection operator. We will get there next day, but before that I thought we will just develop a little less quantitative picture and then only we will go into the complicated one. Okay. So, gamma SALC. So, what Carter has done is that he has represented these 1s orbitals as arrows. After all, this is how the bonds are going to form. Okay. So, you take these vectors, use them as the basis, two-dimensional basis, and construct a representation. You could also think that you take two 1s orbitals. Take two 1s orbitals separately, use them as a basis and construct gamma SALC. That I think we can do without much hassle. The character of E will be 2. What will be the character of C infinity? Where is C infinity? Like this, right? Like this. You are turning this way. You have an arrow, you turn it by whatever angle. What is the character for it? Huh? 1 for each arrow. Correct? So 2. What about sigma phi? Sigma v, what will be the character? 1 for this, 1 for this, right? 1 for this, 1 for this. 2? Which one? C infinity, these are the vectors, right? Where is C infinity? The line joining the two. So I am turning like this. What will be the character no matter what the angle is? 1 for this, 1 for this, right? Turn this way, 1 for this, 1 for this, right? So E is 2, C infinity is 2, sigma v is 2. What about I? We are now considering them separately. If you perform I, what will happen? Like this, right? They will interchange. This and this will interchange. This will go here, this will come here. What will be the character? Are you all okay with this? Mehak, question? 0. S infinity? S infinity means you rotate by whatever angle and then deflect by the horizontal plane, deflect with respect to the horizontal plane. Once again change in place, so once again 0. Alright, okay, got it. C2. This is C2. Alright, this is C2 axis. How will I show another C2 axis in between? Otherwise, this is C2 axis. If you rotate with respect to it, what do you get? They interchange once again. So what is the character? 0. Nicely symmetric, right? 2, 2, 2, 0, 0, 0. Now, what is the next step? You have to break this thing down. This is a reducible representation. You have to break it down into constituent irreducible representation. You know the formula, do it quickly. Do it using the formula. 1 by h sum over r chi I r. H is infinity, so that formula won't work. That is why I wanted to you to use it. Otherwise, if you don't even try, how will you know that it won't work? It won't work, right? So our old faithful relationship does not work for an infinite group because h is infinity. Multiply by 1 by h, everything becomes 0 anyway. That is not going to work. Does that mean you cannot break this down? That is not right. You can break it down. It is just that you have to do it the hard way, by inspection. Okay. So what we need to do is we need to take a look at the character table, right, and we see what is it that gives us 2, 2, 2, 0, 0, 0 when you add it up, and that is the answer you are giving. There is a reason why I have written D2H in the bottom. Don't look at it now. What will give me 2, 2, 2 and 0, 0, 0? Which two representations added together? Don't say A1G, forget about this. This is just that what this guy has written to make things complicated in a simple manner. So sigma G plus sigma U plus, isn't it? Sigma G plus sigma U plus. You have to do it by inspection, there is no other way. Right or wrong? So what you get is, you get gamma SALC equal to sigma G plus sigma U plus. Now what we can do is, we can try to see what are the combinations that are there. Now you already know the combinations here. When I take it as a combination, okay, I have already combined them. What will be the symmetry of this? It will be sigma G plus, right? Don't get confused here. It is true that in inversion, this and this will interchange places, but I have already combined them. So it is now not a two-dimensional representation, it is a one-dimensional representation. It does not matter if this plus go to that plus, character is still 1. Do you agree that this is going to be your sigma G plus combination? Agree or not agree? Agree?
If they interchange, the character is going to be 1.
Yes.
But in case of inversion, these two interchange and we have taken 0.
Right. In that case, what we did is, we took them as two separate vectors. We had not performed the linear combination yet. Right? We took them in their unmixed form. So there are two vectors, right? Two vectors, two atomic orbitals, separate. So the basis is two-dimensional. When we invert, one goes here, this second goes there. That is why the character was 0. Now I am taking the linear combinations, right? So I can write this like psi equal to psi 1s h dash plus psi 1s h double dash. If I take this, they are in any case separated by some distance, right? Beryllium has to come in between. So if I take this, what is the dimensionality of the representation now? 1. We have already performed the mathematical combination. So when it is 1, then it does not really matter if these two change places. Okay. Now they are not being considered separately, they are 1. Okay. That is why character is 1. Alright. Can I go ahead now? Fine. So this is sigma G plus, and what is the other one? Sigma U plus. Sigma U plus means what? Sigma U plus is 1, 1, 1. With respect to I, it should be minus 1. With respect to C2 dash, also it should be minus 1. So without much ado, I can write the other combination as plus and minus. This is your sigma U plus. Okay. So I have got this. Now what I do is, I combine suitably with the atomic orbitals of the central atom, and we generate the molecular orbitals. Alright. So we have done two things so far. First is, we have done the entire exercise even without using character tables. And then we have done the same thing using character tables, which is not really necessary here, but the reason why we do it is to show how character tables can be used to generate such combinations. Now let us take a little more difficult example. How can we make it more difficult? One is by adding pi bonds, the other is by taking your adding more atoms. But before that, let me just show you the molecular orbitals that are generated once. There is one more thing that I wanted to say. These are the MOs that are generated. Look at this. Is it not the sigma G plus orbital? Sigma G plus symmetry? Right? What about this? What is the symmetry of this? sigma u plus, isn't it? Right or wrong? Now I am using these as the basis and trying to see whether I can identify the symmetry species to where these belong. Earlier we have seen that vibrations belong to some symmetry species or the other. Now we are showing you that even these orbitals belong to some symmetry species or the other. Okay. So see, this is sigma g plus, this is sigma u plus. What about this? What is this? The third one, sigma g plus. You understand that, right? What will be the character for I here? The reason why I am saying this again is because when you see plus and minus, you tend to think it is u, it is not. Even here, you start from a minus, go through the center equal distance on the other side, you still get minus, right? It is g. It is once again sigma g plus. And what is this? This is sigma u plus. Okay. So what you have done is you have done a symmetry classification of molecular orbitals as well. These are all sigma orbitals, right? And these are all sigma bonds. So sigma bonds derive their names from the symmetry species where they belong. It is usually customary to write small sigma instead of capital sigma when you are talking about molecular orbitals. Yes, sir.
If we combine the SALC as a whole reducible representation with the molecular atomic orbital of the central atom, we will get a three-dimensional basis.
Yes.
So we can get three atomic orbitals, molecular orbitals.
Okay. And
For getting 4, we have to take these sigma g plus and sigma u plus separately
yes.
and then combine.
So what we do is we want to combine reducible representation with reducible representation. That is the most fundamental. Otherwise, if you combine irreducible representation with irreducible representation, then more often than not you end up with that same problem of redundant coordinates or coordinates that appear in more than one kind of thing, because you are taking an incomplete description many times.
No, but that is okay if we get something redundant. Here we are missing something out. How is that possible?
We are not missing something out, we are getting something extra which would come in the other representation also.
No, if we take the SALC, it is a two-dimensional one.
Uh-huh.
And the third one is one-dimensional for the atomic orbitals of the central.
Okay, all right. So if you do that, then what you are doing is you are only taking one atomic orbital, right? Is that not an incomplete picture? Because S as well as P both can contribute. So in that case also you should take both, right? So that is why it is a little dangerous to work with reducible representations, because you can end up describing your basis as something that is not complete, like in this case. That is why we always want to work with irreducible representations. And also, only when we work with irreducible representations do we get to use the character tables easily. Fine. So next what we will do is we will just increase this, we will talk about pi bonds next day.